Okay, let's conclude the first chapter with some uh, additional information on what are the factors that are specifically important for health, right? This is about health, and we already mentioned that there is a pattern to global warming. Some regions are warming much faster, so Middle East, for example, and Northeast Africa, which are semi-arid, arid, already water problems and hot, and now they will get warmer. Then you have to see what happens to the extremes and so on. So there is a background change. Each decade is getting warmer than the other, and then there are seasonal changes as well. But when we say generally extremes, there are some metrics used to define them as extremes. So for example, if you have a particular location where you have temperature distribution, and each year you get certain maximum temperatures which are not very common, and you can look at the 95th percentile of the warmest temperatures, or in a cold place you can look at the coldest temperatures and see if those numbers of temperatures reaching the 95th percentile are increasing, or the coldest in 95th percentile are increasing, and so on and so forth. And there are many studies. Obviously, this is a very regional problem. For example, here India doesn't show up as a tropical country. You can see these are not experiencing a large diurnal range. What we are looking here is the daily maximum and daily minimum temperatures, and the trend in the daily temperature range, minimum to maximum. So tropical countries don't have much of a range, but when you look at rainfall extremes, India is experiencing massive increases in not only rainfall extremes like greater than 150 millimeter per day of rain, but also they are becoming more widespread, in the sense that the flood scales are now of order 10,000 square kilometers. So this map, which is pretty old and is going to be updated one of these days, I'm sure, but the story remains the same. If you look at the trends, here we are looking at degree C per 100 years. So the top red color is 5 and the top blue color is -5 degrees C per 100 years. The first thing you see is there are regions like the islands which are getting warmer, and also they are drier because these are typically in the colder temperatures here anyways. And again, semi-arid regions with little rainfall getting maximum daily maximum temperature getting warmer. But a big continent like North America, for example, has regions on the central western parts which are getting warmer on the daily maximum, but there are also places where daily maximum temperature is cooling down by 5 degrees centigrade per century. And Europe also has a mix. So these are the things one has to watch out for. But it turns out that if you look at the daily minimum temperature, that is increasing faster than the daily maximum temperature is increasing. That's what you would expect from global warming, that you will hit fewer and fewer colder temperatures. But there are details. For example, there is something called the jet stream that runs across here. Many of you may have heard of it. And it plays a role of somewhat of like a referee between the cold high pressure Arctic air versus the warmer low pressure subtropical air, and it can dip and bring cold Arctic air down, or it can go north and bring the warm subtropical air north. For example, the super hot heat wave that's happening in the northwestern US and Canada here has got a dome that's built up with circulation and is sending some of the record warm temperatures into these regions as well. So you can see this general tendency of minimum daily temperatures increasing faster than the maximum daily temperatures, which gives us, of course, predominantly a decrease in the daily temperature range. This can have direct health impacts, of course, but also indirect health impacts through the fact that cold temperatures tend to kill mosquitoes and other pests, vectors, insects, and so on that can damage crops, for example, not just human health. And reducing the daily minimum temperature combined with other background temperature changes, precipitation changes, can cause lots of direct and indirect health impacts as well. So it's not just global warming. We have to get local and get to the diurnal time scale as well. Zooming back out to broader scale impacts, because warming means winter can arrive later and spring can arrive earlier, we have a systematic increase in the so-called growing days per year. So these are trends in growing season length in days per year. White areas are represent areas permanently covered with snow. Light gray areas represent regions with stable NDVI, which is a measure of greenery or vegetation. So it's normalized difference vegetation index derived from satellites. Okay, dark gray areas correspond to areas for which no trend is detected. But mainly, you can see that there are large parts which are in this greenish reddish colors, large parts, with a few in the bluish colors. So there are regions where the growing length has the growing season in days per year has shrunk, but large part of the higher latitudes, and also here the interface between the desert and the ITCZ, intertropical convergence zone, which is the rain band, and some of these regions here are seeing a mix of growing season getting longer, and some there where the growing season is getting shorter. Okay, so again, these are important for health because phenology, vegetation, allergens, people who are allergic, asthma, and so on, can severely suffer from these changes. And of course, there are impacts on food production, which can be positive, but depends on how warm it gets and how the rainfall is changing. Zooming out to again lower frequencies, this is northern hemisphere spring snow cover, generally dropping, which affects rainfall, marine ecosystems, which affects snowmelt, river flows, coastal ecosystems, and water supply, irrigation, food production as well. Arctic summer sea ice extent is a poster child for global warming, and it's been dropping rather fiercely since about the last 4-5 decades, which is not good news. Because remember, as ice melts, reflectivity drops, more energy is absorbed, so the warming accelerates, which is why you have the polar amplification. There are also water vapor feedbacks, clouds, and so on involved. So that also affects livelihoods, life, marine life, people who live in those cold areas, hunting fish and marine mammals, which is where they get their vitamin D from, which is again related to health issues, right? Change in global average upper ocean heat content. So oceans are getting warmer, and warming is going deeper and deeper. Used to be upper few hundred meters. Now you can find warming all the way down to a couple of kilometers. Global average sea level change. So warming ocean leads to expanding water column and change in sea level. And with increased rainfalls, cyclones, stronger cyclones, you have more storm surges, inundation, and that has health consequences as well. Observe change in annual precipitation trend. The main thing to notice is that precipitation is very local. So you can see noisier signals in general, but there are patterns here in terms of millimeters per decade. This region has gotten wetter, and there are regions which are getting drier. Mediterranean, which is already a semi-arid region, the Sahel belt, which is poor and somewhat geopolitically sensitive as well, parts of India, parts of China, Australia, and so on. So this is for 1901 to 2010 and 1951 to 2010, and you can see that the areas with change and the intensity of the change have increased. Here intensity has increased, and here area and intensity have increased, especially over these regions here and here. Okay, so this is what we have to watch out for, not just extremes but also annual precipitation over land, because in Tony McMichael's book we said climate variability, climate perturbations, precipitation changes, and food production are always key ingredients to epidemics, pestilence, famines, droughts, and so on and so forth. Okay, to quickly wrap up, we use models, which we won't go into, to determine not only how changes have happened and why they have happened. So there are what are called attribution studies. So you take, for example, observed warming, and you take a model, you give it greenhouse gas warming, volcanoes, solar radiation changes, and so on. And then you take those forcings out, because in the model you can do that. And you can show that if you don't have human anthropogenic greenhouse gas forcing, you don't get this warming that's been observed. Okay, whether it's on land and ocean, or in ocean heat content. So you detect the signal that says warming is happening, and you attribute it to a cause, in this case human activities. Okay, we use that to make future projections. These are for different scenarios of how emissions, population, technology, renewable energies will change in the future. This is representative concentration pathway 2.6, which corresponds to additional forcing in watts per meter squared that we talked about, radiative forcing generated. This is the most benign situation, where if we want to keep the global warming to less than 2 degrees centigrade compared to pre-industrial period with a high probability like 67%, then this is the warming we will get. But if we go with business as usual and continue to emit, you can see that there are massive warmings, and this polar amplification still stands very strong, and there are hotspots of warming all over the place, which is not good news. And precipitation projections are a little bit harder, and they are noisier, so model confidence tends to be lower, but you can see that in the low emission scenario, changes are smaller, whereas in the high emission scenarios, changes can be pretty massive, where rainfall is increasing and it's drying in some places. But this increase may come as extreme events and cause crop damage, flooding, and serious health issues as well. Okay, these are the global mean sea level rise relative to 1986 to 2005. I won't go into the details here, but there are several scenarios, and the increase of sea level obviously is larger as you go into the future, so this period and this period, but there is a range of likely. Sea level obviously has to be very local, because global mean sea level rise or even global mean temperature increase don't necessarily translate to what it means for your backyard or your community. So one has to be extremely careful about that. For example, a city like Mumbai, which sits here, what exactly will its sea level rise be, and how will it have to prepare for that? So those are the details that have to happen at local regional scales, and the models are not necessarily highly skillful at producing patterns at very local scales. But there are other ways of deriving local information using past history and statistical relations, or what are called dynamical downscaling, which we won't get into, but you get the idea. So with that context, we will get into the next chapter looking at more on weather extremes and health outcomes. Okay, so this is a short introduction to climate science, climate greenhouse warming, and the future, but we will keep revisiting some of these issues as we go along. All right.